Okay, so here's where we left off last time. So we were looking at scalar line integrals. We saw a couple of examples. I'm going to show you a different one. Just why not while we're here? The question we're going to look at, this is kind of a word problem, but we've got a fence, and you can see the fence right here, and these are kind of the pickets of the fence, if you will. The fence is sitting on top of the unit circle, part of which I've drawn there, right? And notice that the height of the fence is not constant. The height of the fence varies with location. Now, why would we ever encounter such a thing? Various scenarios you can imagine. Maybe you've got a vegetable garden on one side of the property and you want it to get more sun. Maybe you've got a nosy neighbor on the other side of the property and you want to make sure that they can't see what you're doing. Right? Whatever the motivation, the question we're going to try to address is what is the area of the fence? And why would we want to know the area of the fence? By the way, I will note that we usually don't need to know areas, right? That's one of my main things about interpreting integrals, is that it's not that often that you need to know areas. But sometimes you actually do, such as if you want to stain your fence. You need to know how much stain to buy, and of course, more area, more stain. Okay, all right. That said, how are we going to compute this area? And I'm going to make the observation that a little piece of area of this fence is a little piece of a rectangle. Again, approximately, pretty much, round off error, goes away in the limit and all that. And let's see here, how do I compute that area? Oh, let's see here. That area is, I think pretty believably, the height of the fence, which again we know, it's given, times the width of that particular picket, ds. And so, pretty straightforward argument, just a purely chop it up, add it up, right? We haven't gotten to the actual computation yet, how we're actually going to plug and chug and compute this thing. But how would I take the whole question and break that up as a sum of little parts? Goes like this. Does everybody buy it? Okay. All right. So now, how do we compute this thing after all? And by the way, notice we have, of course, scalar line integral, right? Just like we were talking about last time. So how are we going to compute that? Well, we have a process in place for how to compute scalar line integrals. Step one is we parameterize our curve. So keeping in mind our curve is the unit circle, right? That is easily parameterized, like so. Old news, we've done this several times in the past. Okay, so cosine and sine. What are we going to do with that parameterization? Well, we have to pull back through the parameterization, a lot of which is just plugging in. But we do need to know the extra factor here, and that extra factor, of course, is speed. Speed being the magnitude of the velocity, velocity being the derivative of the parameterization. So you got to take your parameterization, take its derivative, compute its magnitude. That's what goes there. Right? Okay, it's like our stretching factor. Oh, let's see here. Let me while we're here. So ds is magnitude of x prime times dt. Reminder: height, previously discussed. Oh, let me get rid of that purple. Height is given to us as that formula. Right, so now it's just really a matter of kind of doing it. There's one last little detail we do have to plug in for. Notice we're trying to build up here a dt integral. We've got everything in terms of t except for that x. And what do we do with that x? Well, we recall that x is one of the outputs of our parameterization. It specifically is the first output of our parameterization. And you can see right here, x is cosine t. And so, again, just plugging in from the parameterization, that x goes away. Yes?
Sorry, where is this parameterization Oh, parameterization coming from again?
Yeah, well, it's just that we've done it before. So I made an argument a long time ago, back in chapter 1, I think it was, that if you want to parameterize the unit circle, then this happens to do it. The argument I made was that these formulas for x and y satisfy the equation that I know that x and y satisfy on the unit circle, namely x squared plus y squared is 1. Yeah, yes.
So I'm assuming the interval is like 0 to 2 pi because you're going around the circumference. So how would you find that if you didn't have an intrinsic idea of what it looks like?
Yeah, I mean, you do have to have a certain amount of understanding of what your parameterization is doing. It's all, if some form or another, it's going to come from understanding your parameterization. And here, I know that my parameter is basically angle, and then I just think about the angles. Yeah. Yes.
Really quickly, just one more time about the stretching factor.
Yeah.
Do you think about like your chain ruling because x is dependent on t, so since you're taking like a dt, you have to also do dx.
It's not that far off from that. Yeah, I mean, it's technically a little bit different because x is a vector, not a scalar, right? And we're interested in magnitudes, not quantities exactly, right? So, I mean, it's not that far off, but if you look at the argument that we made, I guess the way I said it here, I just pretty much directly argued that distance equals speed times time, right? But yeah, underneath all of this, you could view this as a vector displacement is a vector velocity times time, and then just take the magnitude of both sides. Yeah, totally. Yeah. Okay. So it's basically all over but the shouting. I'm going to leave the details to y'all. And this fully single variable integral, y'all can crank out on your own. Yes?
One more thing. Just from reading the question, how did you know that you wanted to parameterize it using a circle?
Because I was directly told that the fence is on the unit circle. Oh, okay. And so, the path that I'm building the fence on top of it was given. Yeah, right. Yeah. Okay. Another example, or so it will seem, for at least a couple of minutes here. Suppose I have some path, and I want to compute the amount of work that it takes to move along this path. Now, let me just remind you, as of the moment, what we've noticed so far, this has got all the earmarks of a scalar line integral problem. There is a curve over which something's happening. That something is an accumulating quantity, right? Work. Total amount of work is the sum of the little pieces of work. So, chop it up, add it up, and each little piece, relatively easy problem, and all that from there. So it does seem like this is going to be a scalar line integral. There are some nasty little details here, though, that make it actually not turn out that way. So anyway, that's a little bit of foreshadowing. Let's look at the details here. We have an existing formula for work. This already was an improvement over the high school formula for work, which was just scalar force times scalar distance, and then an asterisk followed by a paragraph where you have to talk about, we're interested in the component, and so if these are not in the same direction, then blah, 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 right? A lot easier just to recognize that force is not a scalar. Force is intrinsically a vector. It has a direction. It's a vector, right? And then likewise, displacement is not a scalar distance. It's a vector. Displacements have a direction. Anytime I walk 10 feet, I walk 10 feet in some direction, right? So again, naturally thought of as a vector. So this formula that I have circled here was already an improvement, but it does have some problems. This formula assumes that my force is constant. In the real world, it isn't, typically. Right? It also assumes that I'm moving along a straight line path. Again, in the real world, not necessarily, right? Very possibly could not be that. So we're going to figure out how to take this formula and adapt it to our curvy path with a non-constant force and improve this formula yet again. Okay. All right, so again, we chop it up into little pieces. Let's look not at the whole piece here. Oh, gosh, what is that? Okay, piece of junk. Not the whole curve. Let's look at just this one little itty-bitty little piece of curve. Little bitty pieces of curve are approximately straight. They're small, and so the force is approximately constant. So when I chop this curve up into little pieces, it's going to be a kind of a question that original formula can actually address directly. No asterisks, right? Just fine. Okay. All right. But there is a nasty little detail that we have to worry about here, and that is that what we are adding up here is given that we're moving along this curve in a certain direction. And let's just think practically about this. If this is let's say a windy mountain road that I'm going to be driving up, or worse, hiking up, I'm going to be doing a lot more work if I'm hiking uphill, right, than if I'm hiking downhill. If you're hiking downhill, put on some roller skates and, try to have a cushion down at the bottom that you can plow into. A lot easier from a work standpoint. So totally different with the direction. None of our previous examples have this feature that the direction matters. Just for fun, when you paint a fence, does it use more paint if you go one way versus the other way? No, of course not. That is ridiculous. If you're interested in the mass of some weird shaped irregular wire, does the mass add up differently depending on which order you add up the little pieces? No, that's of course not. Right, so there's something really fundamentally different here. These are truly scalar quantities that we're adding up, but there's something intrinsically, we say, oriented about this curve. It is going specifically one direction and not the other direction. And that difference matters. Is everybody on board? Okay. All right. So we're expecting something different's going to play out. Here are the details. Here's our little piece of curve that we're looking at. Again, keep in mind, chop it up, add it up. We're just looking at one little piece right now. On that little piece, how much work does it take to move across that little piece? Well, I'm going to have a displacement dx vector approximating how much I move, right? And over that little piece of curve, I will be applying some force. And force dot displacement, easy formula, right? Nothing to it. So on each little piece, that's how much work it takes me to do. If I want to add this up over the entire curve, then I do that. Right? The whole is the sum of the parts. Again, as previously noted, dw is f dot dx. So all I'm doing is to chop it up, add it up. And what we have, interestingly, you'll notice doesn't really look like a scalar line integral. And it fundamentally, importantly, isn't a scalar line integral. Now, I'm still adding up over a curve, so it still makes sense to call this a line integral, right? But notice a couple of particularly noticeable things. The differential is a vector. By the way, that's pretty crazy. We've never seen that before, right? An integral where the differential is a vector. First time, right? Likewise, notice that our integrand, also a vector. We have actually seen something like that before, but certainly not in this way. Anyway, because of these differences and because, again, of intrinsically that there is this oriented aspect to the curve itself, we're not going to call this a scalar line integral. We're going to call this, in recognition of its differences, a vector line integral. How we doing? Everybody cool? All right. I can't remember if I said this already. I have leftover Halloween candy. Come up and help yourself anytime. Okay. All right. Let's see here. So now a couple other details. All of this is actually kind of old news. This goes back to chapter 3, and we spent a little bit of time talking about little pieces of curve at the time. Our goal was to be able to compute the length of a curve. right? But the setup is very convenient, and it's already there, so we're just going to take this and run with it. Okay? And check back with Chapter 3 if you want a reminder of where all this comes from. That noted, our vector line integral, I can rewrite it a couple of different ways. For one thing, dx, I can rewrite as x prime dt. And that changes our formula for a vector line integral to a formula that's actually really easy to work with. You look at this second green circled formula here. It's an integral on the t-axis for one thing, right? This does the pullback through the parametrization effectively for us. T goes from A to B. Rewrite all this stuff in the dot product in terms of T, which is literally just a matter of plugging in the parameterization. This is a Calc 1 single variable integral. Very plug and chug convenient. Okay. Now there's another form you can use, if you like, you can make this other observation that dx is also TDS, and we talked about that a while ago. Again, this gives you yet a different point of view on how to write a vector line integral. I personally don't, it's not wrong, it's fine. I don't like it though, right? I don't have to like it. Right? What I don't like about this integral is, you see the ds on the right, it makes it look like a scalar line integral. It's importantly different from a scalar line integral. And I believe that when things are different, they should look different in notations, right? So I find the fact that this writes it in terms of ds as that's a bug, not a feature to me. Right? There's other quibbles I could make, but they're not important, and I'm not going to spend time on them. Okay. Okay, so there we go. We have some formulas, and now we're ready to start plugging and chugging. As you could probably gather from what I just said, we're going to be using these two mostly. Right? So here we go. The question is, we've got wind blowing on us. The wind is, let's say, a strong wind, and I'm having to push. You are having to push forward to prevent the wind in your face from blowing you over backward. Right? Okay. And here's a formula for how the wind is pushing. That said, you're going to be applying forces, to not be blown over, as you walk counterclockwise on the top half of the unit circle. So we have a force, we have a curve that we're following, and we want to compute the total amount of work. And so, of course, work is a vector line integral. We already talked through that. Now, there is a little annoying little detail here you always have to be on the lookout for. It's just, this is the nature of how these things just show up. The annoying little question is, what is the deal with this minus sign right here? Right? And let me explain where that minus sign comes from. This is about equal and opposite forces. Old physics idea, but okay, here I hold up my pen. There are actually two forces acting on this pen. Gravity is pulling it down. I'm pushing it up. Right? Likewise, in this question, there are actually two forces. There's the wind exerting a force on you. It's pushing you, let's say, back, right? And then there's the fact that you are exerting a force forward to oppose that, to keep from being blown over. So the force that the wind is applying to you, the force that you are applying back to the wind, are opposites of each other. They're negatives of each other. Okay. So you've got to decide which one was given and which one do you need. And it all comes from the phrasing of the question. So notice what was given is the force that the wind is exerting. Which one do we need? Do I need the force that the wind is exerting, or do I need the force that I'm exerting? Well, we're asked about the work that you perform. So we need the one, we were given the other, and thus the minus sign. Does that all make sense? Please don't overinterpret from this. Some students just say, all right, for good measure then, I'm just always going to put a minus sign in there. That absolutely does not make sense, right? The minus sign depends on whether or not these are the same or whether these are the opposites. So the point to this is just always think about it, right? Just be on the lookout for phrasing of the question and whether you should or should not put that minus sign in there. Okay. All right. Okay, and that said, again, work as a vector line integral. How do we compute vector line integrals? Well, step two, we parameterize. Here's our parameterization of a reminder here, the top half of the unit circle. Right, the unit circle aspect of it is that formula. Top half is why we only go from 0 to pi. Yeah. Okay. All right. Okay, we know we're going to need our x prime. After all, here it is right here in the formula. Right, going to need to know that x prime. So let's take the derivative of this parameterization. Easy trig. And now it's just a matter of plugging it all in. So here we go. There's the formula from the previous page. This is how we pull back through the parameterization. Right? Notice my velocity, right there. Notice furthermore that carries through our velocity here, like that. Let's see here. This minus sign, it's easy to lose track of that, so go ahead and carry that all the way forward, right? You don't want to accidentally oops that. I do need to write down what my force is. Now, again, we were explicitly given this formula for the force. The force was y comma negative x. I claim that is sine t comma minus cosine t. And where did that come from? Well, it comes from our parameterization. It's easy to forget this. There's a lot going on, a lot of things to keep track of. It's easy to forget that your parameterization explicitly tells you the formulas for x and y. Right? X and y are just straight up given here. So right here, x is cosine t. That's the plugging in part of pulling back through the parameterization. Is x is cosine t. Everybody on board with that? Okay. And then let's see, likewise, what color have I not used yet? How about a little blue here? Y is sine t. So hardly anything happened. I literally just plugging in to established formulas, and it's basically all over but the shouting. Of course, you do have to actually do the dot product. The dot product ends up being 1. Life is good sometimes. You do have to actually compute that integral, world's easiest integral, and there's your answer. Everybody happy? Okay. All right. Oh, whoops. Just get rid of the mess. Okay, you may recall we saw when we were talking about scalar line integrals that you can parameterize however you want. Of course, as it should be, right? I mean, if the parameterization is just a tool for computing the line integral, different parameterization doesn't change the fact that you're still trying to compute the exact same line integral. So it really ought to not depend on the parameterization. It's very nice that it doesn't. So likewise here mostly, except you've got to make sure that when you parameterize the right way. You can't parameterize it backwards. Right? If you're going to be hiking a mountain trail and that trail is going a certain direction, well, your parameterization has to go that same direction. Otherwise, you're entertaining the scenario of going exactly the opposite on each little piece, and you'll get a minus sign in every term in your Riemann sum, and thus a minus sign on your final answer. So do make sure to parameterize the right direction. If you don't, you will be off by a -1. Yeah.
So in this case, if you like move clockwise, would you just be switching the bounds of where you started and where you ended?
I hear where you're coming from. Can I put a pin in that? I'll answer that question after I've done some other stuff, and that'll be an appropriate time. Yeah. Please remind me if I get past the middle of the second page and if I haven't answered your question. Okay. So now let's make a theorem that recognizes this fact. Again, if you parameterize backwards, you're off by -1. There's an easy way to say this. We just first have to kind of make up a notation for what do we mean by parameterizing backwards, and the little minus sign as an exponent. Really convenient little notation there, and what that means is do the curve C, just go the other way. So what this theorem down here says is that if you go backwards along your curve, then you just get a minus sign on the value of the integral. Which again, just what we previously saw. Everybody buy it? Right. Okay. Okay, so here's a question. Let's suppose we are again, top half of the unit circle, and again with the wind, and again how much work do I exert, and again with the, I got to think about the wind is pushing one way, you're pushing opposite of that. Everything the same, only one difference, and that is we're going the other way on the curve. How does this change the problem? And I'm going to show you 3 different ways to answer this question. Kind of 4 different ways to answer this question. I'm going to start with the best one, and that is to say, look, if the direction is the only thing that's different, then I suppose I maybe kind of ought to reparameterize. But here's the thing: I've already computed the integral over my original counterclockwise curve. I've already decided that that's pi. And what I'm doing now, my new curve is just an opposite orientation on the original curve, C. And we know that going opposite direction just gives you a minus sign on your answer. And so my answer has to be negative pi. No, that's the easiest way to do it, in my opinion, right? It's just, boop, just done, right? And I've written it down in 3 separate steps here, which, just to be as clear as possible. But you don't necessarily have to write all that down. Just make sure you write down some indication of orientation backwards, thus, and then point to your minus sign. Does that make sense to everybody? All right, now let's assume you had not already previously computed the amount of work it takes to go the other direction, right? So if you couldn't lean on previous work like we just did, how would you come at this directly, parameterizing in the correct direction? So here's the idea. If I have a point there that I want to visualize as moving clockwise, right, around this top half of the unit circle, then,
Did you just take that point arbitrarily?
Yeah. So when you move, right, you're going to cover all those points, and I just picked an arbitrary. Yeah, totally. So as you're going in this direction, I'm going to say that this is my parameter t, in the sense that this is where t is equal to 0, right? And then as time passes, this is where t is going to be pi. And that'll take me as required in the clockwise direction. Okay. All right. So with my parameter established, if I want to write down a formula, for position, how am I going to find this position, x comma y, as a function of t? Trig ensues. Right? And you can, I suppose, try to make an argument directly about looking at that angle t and thinking about, how would you interpret the resulting little triangle or whatever. I think an easier way, and what I would encourage you to do, is to just recognize that this angle is pi minus t, and more to the point, is theta. So forget the blue angle for the moment. Theta is the known established convention for how I write, you might say how you convert from polar coordinates to rectangular coordinates, right? And so I can immediately, effortlessly write down that x and y are cosine and sine of theta. Is that cool? And then angle addition formulas or trig symmetries, or however you want to think about this. But once you know that you have these formulas, then you can rewrite as this. And this then is your final answer. Reminder, I do think it's important that every student in this class should know angle addition formulas. I'm going to call that a requirement of the course. They come up a lot. They're really useful. They're going to come up a lot in your engineering and physics courses as well. So might as well know them now. All right, so that's one approach. Now here's a different approach, perfectly reasonable but different approach would be to say, okay, well, I'm, again, interested in parameterizing like this, but the thing is, I already know how to parameterize like that, right? Cosine t, sine t. Counterclockwise? Yeah, that's our old friend. We've done this a million times, right? So, what's the relationship between these two parameterizations? The blue one going like so, the green one going like that. I think it's geometrically pretty clear. They're reflections of each other over the y-axis. Right? Is everybody okay with that? And so, okay, so again, pretty straightforward. If you want the blue parameterization, then what you're going to do is literally take the reflection over the y-axis of the green parameterization. And what does this reflection do? What's the whoopsie? I guess I should have it going the other way for one thing. If I reflect over the y-axis, that reflection just adds a minus sign to the x-coordinate. So a couple of different ways to think about it. Now, why am I showing you multiple ways to answer one question? Well, tools for your toolbox, right? You never know when one or the other of these might be exactly what you need. And again, in this circumstance, they both work. In other circumstances, one or the other of these might make more sense. So good to have both of these ideas ready to go. Okay, your question. Can we instead take the calculation that we've already done? Let's see, where was it? Oh, yeah, here. The calculation we've already done and just say, look, 0 to pi, right? T going from 0 to pi represented counterclockwise. If I want to go clockwise, I'll just let t go from pi to 0. Right? Now, that will give you the correct answer. Keep in mind, it's not about the answer, it's about the reasoning, right? I'm going to point out two things. First of all, that is morally equivalent to just saying, yeah, it's the negative. Because when you switch the bounds, that does give you a minus sign on the result. So I think it's more elegant to just cite this fact that opposite orientation means minus sign. And that's just sort of more direct. Does that make sense? Yeah. Okay. My other quibble is that if you do this, and you say, okay, yeah, I'm going to have t go from pi to 0. Well, keeping in mind that t, we very often think of that as representing time. Now we're talking about time travel. And I think it's a good idea to stay away from invoking the concept of time travel when you're solving problems. Does that make sense? Yeah. Yeah. Anyway, enough said. Yeah. Okay. Okay, so next question. We've got this new construction, vector line integral. The motivation for this construction was in the context of assuming that our vector field represents forces, and we wanted to figure out how to compute work. Okay, but not every vector field represents forces. Sometimes they don't, right? Sometimes vector fields represent other things. For example, the vector field might represent a fluid flow. if the vector field represents a fluid flow, there's no forces. If there's no forces, there's no work. So what does a vector line integral mean? How do I interpret that in this other sort of physical scenario where I've got a vector field representing fluid flow? And I'm gonna stick with the fluid flow as representing velocity, which just works out nicer in this case. So what is a vector line integral in this context? This is a bit of a discussion, as it turns out. It's a little bit weird. I like it, and I'm pretty sure y'all like it, when we start off with a concept that we already know we're interested in, and then we just come up with a way to compute it. Like, let's compute the amount of mass in something. That's a relatable question. We know why we'd want to compute mass, right? What is going to turn out to be the answer to the question that we're asking here is not a physical concept that we already know we care about. It's something different, and it's something that's hard to even really entirely visualize why I would care. But it does come up a lot. It's just, so anyway, it's a brand new idea, and it's going to seem a little bit weird. So I'm going to ask for your patience, ask you to bear with me as we go through this argument. By the way, all of this right here is just a recopy for convenience of reference when necessary. There's nothing new happening there. So here's the beginning of my argument here. Oh, and I forgot to hit the button. There we go. Okay, this is going to seem to come out of nowhere. I have a curve. I mysteriously am going to talk about an area here. And I'm going to imagine kind of dragging that area along the curve, and it will then kind of sweep out, if you will, this sort of tubular region there around our curve. And I know that's weird. The question I'm going to ask is right here. Hard to imagine, again, why I would ever care about such a thing, but again, this is going to it's going to come together in the end, so again, please bear with me. Looking at all of this fluid in this thin region, this yellow sort of tube around our curve, looking at all that fluid, to some extent, as the fluid flows, the fluid will be flowing along the curve. Now, also, to some extent, as the fluid flows, maybe it's flowing this way, to some extent, it'll be flowing perpendicular to the curve. That's the part I don't want, right? As the fluid flows, I want to look just at the part flowing along the curve. And I want to add that up over this entire yellow region. It's weird. But again, I get to ask the question if I want to. And again, it's going to turn out this is going to actually be very natural. Okay, so with that setup made, this is a very direct computation. I'm going to take all of my fluid. I'm going to break it up into little pieces. Here's a little piece of my fluid in my region R. Again, keep in mind our region R is something like this. So there's a little piece of it. And if the velocity of the fluid is the vector field F that I have in that picture, then, well, the extent to which it's flowing along the curve is this component. So for that little piece of volume, dV, which of course is area times thickness, times this component, which of course is a dot product with the unit tangent vector. Volume times component tells me, for that little piece of curve, how much of the fluid is flowing along the curve. Again, still not clear why we would care about this thing, but that's how you break it up into teeny tiny little pieces. As always, we're going to take this calculation that we've done here on the little piece. We're going to add up over the entire curve. Keep in mind our curve goes on and on like that. So adding up over the entire curve turns this into an integral. And then if you just take this dq that we just computed and plug it into there and kind of move things around a little bit, we get a total answer to the question, which is still not satisfying because it's still not clear why I would care about this. But nevertheless, the total amount that the fluid is flowing along the curve is this expression right here. It's the area times, and now the eyebrow raiser, a vector line integral. So this is what's going to allow us to actually make our interpretation. I'm going to take this equation that we've just established. Notice that the vector line integral is part of it. I'm going to notice, of course, that area is the other factor. Now let's just kind of do a little hand waving about this cross-sectional area. I mean, the bigger the area, the bigger the tube, the more of the fluid, and therefore the more of whatever this thing is that I'm computing. So of course it's proportional to area. That's not that interesting. That's not what we're trying to understand about the fluid flow. So I'm going to factor out that area by saying, look, I'm going to interpret all of this, per unit area of the cross section. Of course it's proportional to the area. So per unit area, the line integral represents the, in some sense, combined extent that fluids flow along the curve. So this weird question that we asked is actually the answer to our original question. How in the world do I make sense out of vector line integrals in the context of fluids? Well, in the context of fluids, line integrals compute how much the fluid is flowing along the curve. Everybody all right? All right. So there is a special case that's very important to discuss. The special case is called circulation. The specialness of the special case is that this considers only curves that are closed. Curves that start and end at the same point. When you have a curve that starts and ends at the same point, the vector line integral goes by the name circulation. And I'll be able to tell you some incentive for that terminology, like where in the world do we get this term circulation from? I'll be able to motivate that in a couple minutes. But first I want to walk you through some examples. We're going to take advantage of this idea of understanding line integrals as representing the extent to which fluid is flowing along the curve. So here we go. Here's an actual scenario. Let's look at this this curve right here. Counterclockwise circle, notice. That is a closed curve. Starts and ends at the same point, right? And let's imagine that we have a vector field like this, and et cetera, all the way around. And now, just intuition-wise, I mean, what do we feel like this line integral is going to add up to? What does this line integral look like in that context? Well, we're going to look at little bits along this little piece of curve along in here. Notice the curve is going like that. Notice the fluid is going like that. So I think it's fair to say here, on this part of the curve, the fluid is flowing along the curve significantly. Maybe not perfectly. Maybe it's the angle's off just a teeny tiny, whatever. But basically, mostly, the fluid is flowing along the curve, including thinking about the orientation. It's not flowing backwards from the curve's direction. It's flowing the same direction the curve is going. Likewise, everywhere else along this curve, right, we're going to have a positive extent that the fluid is flowing along the curve here. And et cetera, all the way around. So grand total here, looking at this picture, grand total, how much is the fluid flowing along the curve? Well, pretty positive, right? Pretty significantly positive. And so I'm going to say that our circulation is positive. There. Is that cool? Okay. Now, this is a nice example, by the way, of why we use the term circulation. So if you think about the geometry of this idea of a closed curve, if I imagine starting here, it starts going like this, and then it kind of has to loop around on itself, as it were. Right? To be more precise, the unit tangent vector, as I go around, and now imagine I was looking just at the unit tangent vector, forget about the curve, looking just at the unit tangent vector as it goes around. The unit tangent vector literally goes around in a circle. Right? Okay, cool. Closed curves kind of go around in a circle. No surprise. Keep in mind what this line integral is computing. The line integral is computing the extent to which the fluid is doing the same thing. Right? Again, the extent to which the fluid is flowing along a curve that goes in a circle. And so thus, to some extent, the vector line integral is measuring the extent to which the fluid tracks something that is going in a circle, and thus the term circulation. Everybody buy it? It's not a rigorous argument. It's just a kind of a hand wavy satisfaction about the terminology. All right. Okay, another example. Here we have a curve going the other way, you'll notice. You'll further notice we have the same exact fluid flow here from the previous example, etc. all the way around. And now let's just kind of think it through. What can we say about circulation here? Well, one little piece at a time. You can see from the picture, I hope, that everywhere along this curve, the fluid is flowing opposite of the direction of the curve. It's not going along the curve, it's going backwards from the direction of the curve. So, and keeping in mind that we're looking at dot products, when you have vectors that are pointing in opposite direction, the dot product's negative. Right? So each little piece of the vector line integral along this curve is going to be negative, and so for this one we expect our circulation to be negative. Is that cool? All right. And then sometimes it's really hard to tell. So if you look at this example over here, it's just a weird one. There's the curve. In some places, the fluid flow is backwards of the direction that the curve is going. In other places, the fluid flow is positively along the direction that the curve is going. So keeping track of this integral, we're going to have some positive terms, such as on the right side here. We're going to have some negative terms, such as we would see over on the left side. How do these positives and negatives balance out? I don't know. It's hard to say. You really have to work out the integral, right? And by the way, there is another technique that we're going to see later on next week, in fact, that will help us address this. But I'm going to leave this for the moment as question mark, because looking at the integral as we're interpreting it here, it's just not clear. Okay. All right, now there's a nice interpretation of circulation. This is hand wavy and imprecise, but I think nice. I am going to consider a small object here. Small means that I'm going to claim that there's a certain amount of uniformity. Stuff just can't change that much over teeny tiny little distances, right? So on a small object, such as, for example, by the way, this being right in the middle of fall, I'm going to imagine an orange fall leaf that has dropped down into some flowing water, right? As you might see in a little creek or something. So our little small leaf I claim that circulation is going to kind of tell us how this leaf is going to be sort of rotating as it moves through the fluid. Because after all, as we saw previously anyway, in this case, the fact that the fluid flow is going in the same direction as the boundary, this is going to be pushing the leaf counterclockwise. Likewise, over here, the fact that the water is going that way is going to be pushing the leaf counterclockwise, et cetera, all the way around, right? Like over here, this part of the flow is going to be turning the leaf counterclockwise, all the way around counterclockwise. Now, to be fair, circulation only considers the boundary. What about all that interior? The water underneath the leaf is pushing it as well. And this is where I'm going to invoke the smallness and say nothing that different happens. And we'll be able to make all this more precise next week. But roughly speaking, that there's nothing dramatically different about what's happening on the inside versus on the outside. Yeah, in the back. Yeah.
Does this relate to curl?
It does. That's a great observation. The details of that are going to take us quite a while to work out. But yes. Yeah, totally.
Okay, but to be clear, on the test, we're going to see curl and divergence, but we're not going to be seeing it in this.
Nothing we're doing today is fair game for the test.
Okay.
Yeah. Monday was the cutoff for, to be more precise, section 5.6 is the last fair game material for the test. Yeah.
Okay, but what would be like the difference between what we saw in curl versus this?
The difference between what?
Like what we saw with curl.
Oh, yeah, no, very little. I mean, you put your finger right on it. No, curl's very closely connected to what I'm claiming here. And we're going to see, and I can make that connection, we're just not ready to make that connection yet. It requires a theorem we don't quite have yet. But no, your intuition's perfect. Is that what you were going to ask?
Yeah.
Yeah, okay. Yeah, okay. Cool. All righty. So real quick, let's see, and I know I'm short on time here, but I think we can get through at least this example. Every so often you get lucky. I think it's really important to be aware of the awesome opportunities that arise here and there. Now, I've already given you my biggest pitch on this, and that's the symmetry theorem, specifically the odd symmetry theorem. Right? And there are others that are not as useful. Odd symmetry, I think, is where it's at. Right? So that's why I pushed that one. This next category of things to be on the lookout for, where there's big payoffs, that'll save you tons of trouble. Maybe not quite as much as symmetry, but still going to save you tons of trouble, right? Is luck with geometry. So here is a, on its face, horrifying question. Just horrifying. Look at this nightmare, right? We've got the my parameterization that I'm using to describe the curve isn't even rectangular. This is a spherical parameterization, which means x, y, and z are going to involve sine and cosine of this phi and sine and cosine of this theta, right? Our vector field is going to have those nasty formulas for x, y, and z. Well, they go into your vector field too. Right? This is a nasty question on its face. Yeah? Everybody convinced this is a nightmare? So, sure would be nice if we can see a clever way around this. Here's the clever way around it. Innocent observation. This parameterization, for all its horrifying features, is entirely on the unit sphere. And if you are moving on the unit sphere, then your displacements are always parallel to the sphere. Right? I mean, it might be an ugly formula for the displacement, but it's parallel to the sphere. Okay, now let's look at the vector field. We've got this vector field here. Notice that the vector field is a scalar multiple of our position vector. And again, our position is always on the sphere. Well, your position vector, like so, right? Keeping in mind the vector field is a multiple of that. Our vector field is going to, I don't know what the magnitude is or how the magnitude varies. Oh my God, I don't know. But I do know that it's a scalar multiple of the position vector. And side note, spheres are awesome. Gotta love spheres. The position vector for a sphere centered at the origin is always perpendicular to the surface. This is a unique feature of spheres centered at the origin. The surface is always perpendicular to the position vector. So that means that our vector field is always perpendicular to the sphere. So when we look at this dot product in the integral, right, this dot product that makes up most of our integral, that dot product is between two things, one of which is parallel, one of which is perpendicular. Therefore, they're perpendicular to each other. Dot product is 0. Drop the pen, walk away. Right? This is awesome. We just saved ourselves just an unimaginable amount of trouble. So all the credit goes to the fact that there is a very powerfully convenient geometry of spheres. The fact that this is a sphere is what makes it all come together. Be on the lookout for these kinds of awesome little coincidences. And we'll draw the line right here and pick up here on next week, right? Don't forget, exam on Friday. See you then. Good luck with your study. And again, don't forget about grabbing some Halloween candy on your way out.